In this video, we're going to link together two concepts. One is a clearly chemical concept, and that's stoichiometry, and the other one is electrical current, which is more of kind of a physics thing. So let's define electrical current. Electrical current is the rate of flow with respect to time of electrical charge. So if charge flows through a wire, which is measured in coulombs, that's an electricity thing, and you measure time in seconds, a coulomb per second is an ampere of current. So imagine, you pick a point on a wire, let's say, or any conductor, and charge flows through that point a certain number of coulombs per second. That's the number of amperes that are flowing through there. By definition, in terms of symbols, I is current. Current is the change in charge divided by the change in time. So an ampere is a coulomb per second. In chemistry, we think about electrical charge as being quantified by the fundamental unit of the charge on an electron. So to put the charge of an electron, which we think of as like 1 minus, into terms of electricity, the charge of an electron is 1.6 times 10 to the minus 19th coulombs. You might remember that Robert Millikan discovered that in his oil drop experiment from a previous video. So if we wanted to know what was the charge on an entire mole of electrons, we can just do a little dimensional analysis thing. There's 1.6 times 10 to the negative 19th coulombs for one electron, but there's 6.022 times 10 to the 23rd electrons per mole of electrons. And when you multiply these together, it comes out to 96,500 coulombs per mole. And that's a number that we call Faraday's constant, and it's symbolized by this scripty looking F kind of a thing here. So Faraday's constant gives us a link between chemistry units of moles of electrons, or moles of anything that could be related to electrons, and the electrical quantity of coulombs. So remember, current is defined as the amount of charge that flows past a point in a given time, which is given by this equation here, I equals change in charge over change in time. And for every mole of electrons, the charge is 96,500 coulombs. So if we multiply both sides of this equation by delta T, we find that the current times time is charge, but also we realize that charge is equal to the number of moles of electrons times Faraday's constant. So if we equate these things, we have a relationship that links current to moles. Let's use this in some practical applications. Say we're doing an electrolysis and forcing this reaction to occur where chromium is going to be reduced from chromium 2 ions. The question is, if 0.86 grams of chromium has to be plated onto this faucet in 12.5 minutes, what current is needed? So the current is what we're trying to find here, which is a number of amperes or coulombs per second. That's the direction we want to go. First of all, we're going to need something that relates moles of electrons to moles of chromium. And so we'll need the reduction here. Chromium 2 plus is reducing to chromium, and that's going to require 2 electrons. So for every mole of chromium that we form, we have to pass 2 moles of electrons through this system. So I'm going to do this by dimensional analysis. This usually works out really nicely by dimensional analysis. I'm going to start out with 0.86 grams of chrome, and the molar mass of chromium has to be used here because I need moles. So for chromium, that's 51.996 grams per mole. That gives me moles of chromium. But for every 1 mole of chromium, I need 2 moles of electrons. That's the stoichiometry between chromium and electrons from that half reaction. And then Faraday's constant tells me that every 1 mole of electrons carries 96,500 coulombs of charge. So that means if I multiply all this stuff together and divide, work out the arithmetic, it's 3,192 coulombs are needed. So what current do I have to have? Well, I need 3,192 coulombs, and that has to happen in 12.5 minutes. So that would be 12.5 minutes, and then there's 60 seconds per minute. We need that in seconds because We want amperes, which is coulombs per second. And so this will work out to exactly that, coulombs per second, or amps. And when you do all the arithmetic, it's 4.26 amps are needed. Another question: what volume of F2 at 1 atmosphere and 25 degrees C will be formed in 2 hours? So now we're starting from a time quantity, 2 hours. Current is going to be in coulombs per second, so let's change that to seconds. 1 hour is 3,600 seconds. Our current here is 10 amperes, so that means 10 coulombs per second. So now I've got coulombs. Remember that there's 96,500 coulombs per mole of electrons. And then if we think about the reaction that's happening here, this is F minus becoming F2. So we're going to need 2 moles of F minus. And when this oxidation occurs, we're going to release 2 moles of electrons. So that means there will be 1 mole of F2 gas formed for every 2 moles of electrons. And so this works out to 0.373 moles of F2. We want a volume, so we can use the ideal gas equation to model this. V equals nRT divided by P. So that's 0.373, I'm going to leave the units off, moles, times R, 0.0821 liter atmospheres per mole Kelvin, times the temperature, which is 298 kelvins, because that's what 25 degrees C is, and it's at 1 atmosphere of pressure. So this works out to 9.13 liters. Here's another question. In 1,397 seconds at a current of 6.5 amps, 1.41 grams of metal M is formed, and we're supposed to identify M. Probably the best way to do this is by finding the molar mass of M. So we already know the mass. Let's figure out how many moles are associated with that. Again, we're going to turn to dimensional analysis. 1,397 seconds. And remember, I want to get to moles of metal M here. So what do I know? I know that the current is 6.50 coulombs per second. That's 6.50 amps. So that tells me how many coulombs of charge flow through this system. And there's 96,500 coulombs in every mole of electrons. Now, if I look at the fact that chlorine is a 3-to-1 ratio with this metal, that means that this metal is a 3+ charged ion here. So that would mean that it's going to have to gain 3 electrons to become the reduced metal. So that means 3 moles of electrons go with 1 mole of whatever M is. So now coulombs are dropping out, moles of electrons are dropping out, and this tells me how many moles of M get produced under this current for this time. And the number is 0.0314 moles of M. So the molar mass of M is 1.41 grams for 0.0314 moles, and that's 44.95 grams per mole. Then if I look at the periodic table, scandium is the element that has the molar mass closest to that.